Derka from Zircuit, who is going to be discussing sequencer level security.
Awesome. Thank you very much. So welcome, everybody. As said, my name is Martin. I am the technical lead and co-founder at Zircuit, and I will be talking about how we treat security at Zircuit and its sequencing protocol. So when you now look at blockchains, what is the state of art for security that they offer to end users? When you take a transaction, you broadcast it to the blockchain, to your favorite node, right? And then the node does a whole bunch of stuff. It checks that the payload it received is well formed, that it actually is a transaction. It will check that the transaction is properly signed, and it will also check that the transaction is valid for block inclusion, right? So it will check that we have the proper nodes that is expected for the account that is trying to transact, that it has the proper chain ID, so the transaction was actually meant to be transacted on this particular blockchain. And then it also checks some other stuff that is introduced by various fork rules and similar things. So the bottom line is that the nodes, they actually secure everything that is important from the chain, right? They follow the block formation rules, and they secure the chain by forming the consensus on the content. What they do not do at all is security for the users. They do not care what is contained in the transaction and what the transaction will actually result in, right? So what is this talk about? This talk is about Zircuit and its sequencing protocol because it works a little bit differently. It brings security to the level of sequencer. And this talk specifically is about how we do this with very minimal impact on principles such as censorship resistance or data permanence and redirection of the chain. Okay? So before I go deeper, let's take a look how transactions normally flow through a rollup. Okay? So you are the user. You have a transaction. This is what I'm depicting by this little note, right? So you take this transaction, and the transaction goes to some blockchain node. Then, in the context of rollups, we actually have one system component, one service that is called the sequencer. And the sequencer is responsible for collecting transactions, and whenever it has enough of them, it poops up a block, and it appends this block into the blockchain, okay? So this is my L2. And this keeps happening for a little bit longer. I also have my L1, and at some point when we have collected enough blocks on the L2, we take the state root that represents the current state, the current tip of my L2 blockchain, and roll it up into some smart contract on an L1. So this is the process, how it normally works. Here I'm going to make a pause, because in Zircuit, we clearly do this slightly differently. So this is the high-level concept of what I'm going after. And then in the rest of the talk, I will be explaining the details, how it actually works in the nitty-gritty, okay? So on Zircuit, the beginning is exactly the same. You have a transaction, and you broadcast it to the blockchain. Somehow this transaction makes it through the peer-to-peer mechanism to the sequencer. But before the sequencer includes it into the next block, it is actually going to scrutinize it. It is going to ask some kind of an oracle whether this transaction is safe for block inclusion with respect to the user. So is this transaction here to hack something, or is this transaction here to not hack something? And if the answer is that the transaction is safe, then everything happens the same way how it would happen normally. So the transaction will be included in the first available block, and everything is fine. If the oracle responds, no, this transaction is here to cause some damage to the users. It is here to hack your favorite protocol or do something that we do not really consider cool as users. Then the sequencer is going to handle it differently, and we want for the sequencer to put it into the quarantine for some time. I'm going to elaborate on what exactly this means in a few seconds. Okay? So the malicious transactions go into the quarantine. The honest ones and benign ones go directly into the blockchain, and the rest of the process is exactly the same. We will be waiting for sufficient number of blocks to be formed, and then eventually take the tip of the chain, and in the form of the state root, we are going to roll it up. So now, if you're a developer or somehow technical, you must have a whole bunch of questions. How exactly are we doing that, right? So what exactly does it mean that we place a transaction into the quarantine? what happens with that transaction once it has been placed into the quarantine. How do we actually tell if this transaction is malicious and it should be placed in the quarantine? And then we also have some specific or special types of transactions. I'm going to call them here deposit transactions from L1 that, if you know something about rollups, also require some kind of a special handling. So I'm going to address these topics in the rest of the call. So the first question, what the hell is the quarantine in the first place, right? So now I'm going to sort of switch from the generosity into the specific implementation that we are following in Zircuit. So Zircuit is actually implemented based on Geth. Now, when Geth handles transactions, it follows this simplified lifecycle. It maintains two pools. One is called queue, and the other one is creatively called pending queue. So, we have a little bit of term overloading in here. But the bottom line is, I have a transaction, and it goes into what I call queue. All the transactions that are valid transaction, proper payload that belong to the proper chain, will be placed in this queue. But the fact that I have received transaction, it doesn't mean that this transaction is ready for block inclusion just yet. For example, the transactions from individual accounts, they have to be included in blockchain in the right sequence, following the non-sequence without any gaps, right? So if the transaction has a nonce that is way, way, way in the future, Geth will keep this transaction inside of the queue up until it receives the transaction to fill up the gap, and then eventually it is going to be ready for inclusion in the block. So there is this validation happening, and the transactions that are validated and marked as ready to be included in the next block then make it into the other pool, which we call the pending queue. Okay? And then from the pending queue, Geth just selects the best transactions and forms the next block. So this is what happens in Geth. So when we ask what is a quarantine, we need to understand how when we actually query the oracle and where the quarantine sits in the system. And it's between the queue and the pending queue. So on top of the regular validations, whether this transaction is ready for inclusion in the block, our system also asks at this point the oracle, hey, is this transaction okay on top of being ready to be included in the block? And if the answer is no, it's not okay, then it's going to place some flag somewhere in the data structures that Geth maintains, which means, hey, whenever you're considering moving transactions from queue into the pending queue, skip this one. Don't move it into the pool that is ready for immediate block inclusion. So that is what it means to place the transaction into quarantine. We set some kind of a flag that says, hey, skip this, don't include it, and don't move it into the pending queue. So what happens with those transactions when they are placed in the quarantine, right? If I left the transactions in the quarantine forever, that would be some kind of censorship, right? And we don't want that. So we define a whole bunch of criteria that allow for transactions to exit the quarantine. Some criteria are, fairly straightforward. So we said, hey, no transaction should be in the quarantine forever. We generally don't need that, right? Even when there is a hack transaction that somehow showed up in the mempool, it is enough that the transaction doesn't get included in the blockchain for long enough time so that everybody else can exit the given protocol that is about to be hacked in 24 hours, right? It is enough that the users and general community are able to query the node for transactions that are currently in the quarantine, and that the word can be spread around that there will be an incident and that there is some kind of vulnerability that exists in the given protocol, right? So once we have left the transactions in the quarantine for long enough, 24 hours, 48 hours, configuration dependent constant parameter, those transactions can exit the quarantine, and if they still can be included in blockchain, meaning they didn't start yet violating some other inclusion rules, they will be included. If they started violating some inclusion rules, then Geth has the default behavior of just purging this transaction and dropping it from its memory so that it doesn't get clogged, right? So that's the time criterion. Now, you as the user might not be comfortable waiting for the quarantine to sort of elapse. Say that, you changed your mind and you do not want to wait, you don't want to hack that protocol anymore, you just want to use your wallet again and start transacting, right? So you yourself can choose to actively replace the transaction, because this is how we cancel transactions from mining from blockchains. And this is what we call the replacement criterion. So if there was a transaction already included in the chain, which with exactly the same nonce from exactly the same sender, this meets the replacement criterion, transaction makes it out of quarantine, and it will be dropped by Geth. Then we have failure criterion. So imagine that a transaction is about to hack a protocol, but the protocol gets paused. The transaction will revert, right? That's the principle of pausing. So whenever our system detects that we have a transaction in the quarantine and the transaction is simulated and starts failing, that's fine. We will include it in the next block. It's going to fail, and it cannot hurt anybody. So those are the trivial criteria that are sort of, not very interesting. The criterion that I really, really like is economic criterion. So say that you are an honest actor, you are performing some sort of arbitrage on chain, right? So you are pursuing some arbitrage opportunity. And we unfortunately falsely accuse your transaction from being malicious. Well, in such a case, you are 100% confident that your transaction is not malicious, right? You are not here to hack your favorite lending protocol. Well, in that case, you should have the option of telling us, hey, Zircuit, I think that you are wrong. So what do we actually do? Our oracles are a little bit smarter. They do not just say your transaction is good or bad. If the transaction is bad, they also tell us how bad the transaction it is. So, this is going to cost $50,000 in damages. But if I know that the transaction is suspected to cost $50,000 in damages, then it's absolutely fine for me to give you the opportunity to give me a temporary stake, $50,000. Then I will include a transaction in the block right away, right? Because, if it does cause some damage, I have your $50,000 and I can reimburse everybody who got damaged by this action. And there will be no discussion. We will see the effect of this transaction on chain. If the transaction was honest, your stake comes back immediately in the next block. Our block time is 2 seconds. So, this is really not some kind of long-term lockup or anything like that. So this is our economic criterion. And really, you can imagine a whole bunch of other criteria. We have security companies, we have communities, we have researchers, right? So you can also think of some form of an administrative criterion where we just give somebody the privilege to say, you can release transactions from quarantine by just, signing something, right? So that's the release criteria. Now, what exactly does it mean to release transaction from quarantine? Going back to the implementation of the quarantine itself, we just remove that flag and transaction can be moved from queue to the pending queue from which it can be included in the block. So this is exiting the quarantine, right? Cool. So how do we actually know that transactions are malicious, right? That's a very good question. So I will say this, I don't. We are a blockchain, we are a platform, so we are here to provide a blockchain. But there are many, many companies in the space that provide active monitoring solutions and similar technologies, right? So all of these technologies can be turned into oracles, and we are doing that. So if you don't know how an oracle could work, imagine this. Most of them is currently based on some simulation of transaction and then predictive modeling, machine learning on something like that. So I will take my transaction, I obtain a trace for it, we will see how many contracts it has hit, whether it performs the same thing over and over and over and over, which is actually a pattern that very frequently occurs in various hacks. And so we feed that into some kind of a machine learning model, and it will tell us, yes, this is malicious, or no, this is absolutely fine, right? So that's kind of Zircuit basic. Now I have Zircuit advanced. So I said machine learning, artificial intelligence in generally can hallucinate, right? And we do not like hallucinations. In our case, that could result in somebody being falsely accused from executing a hack. So we want to step up the game, and what Zircuit is going to do, we are going to provide some declarative language where you, as the developer and the deployer of a smart contract, can identify for us the intentions that you had for the smart contract and the invariants that should never, ever, ever be violated in the execution of any kind of transaction. So here, we are actually doing something very interesting because we are opening a very new way of doing clever things with smart contracts. So if you have ever developed a smart contract, you might have used something that is called the only owner modifier. You can make your smart contracts ownable, right? There is a library for that in OpenZeppelin. Many people do it. So what only owner does is that whenever a particular method gets invoked, it checks whether the message sender, which is a context variable, environment variable that we have access to in Solidity, matches the address stored in some slot. But when this happens, there is some bytecode executed, right? So users have to pay gas for it, and you actually have to code the logic into the smart contract, which, depending on what exact logic you are coding in, it can actually be a lot of code, and so on. What we are doing here in this declarative language and invariants, we are essentially giving the developers the opportunity to take this thing away from smart contracts. Because in this new setting, we would allow you, through this language, to say, hey, my invariant is that this particular method can only be called if message sender equals this. And you will make that known to the sequencer without the necessity to have that bytecode present in your smart contract itself. And then the sequencer will simulate every single transaction. If it notices that it actually violates the invariant, you have the certainty that it will not ever be included in the block, which can lead to simplification of many projects, right? So it essentially opens a whole new paradigm. And the bottom line here is that, us as Zircuit, we don't have to have a single oracle. We can work with multiple oracles, right? And one thing that you can be certain about is that we will have a very good data set. We will have the entire history of our blockchain. We will have the entire history of our other blockchains where hacks were executed in the past. So we can take this data, we can somehow publish it to all the security researchers, be it independents, academics, industry partners, and we can say, hey, do you have an oracle? Do you think that this is actually better than whatever we have? Well, let's see, backtest it, right? We don't have a problem of including more. So that's a way how we are going to engage the entire community. Final topic for me, L1 deposit transactions. So if you know anything, for example, about Optimism Bedrock, or in general about any kind of rollups, you might know that the transactions that operate with the canonical bridge, so they bring Ether from L1 onto L2, they have some kind of a special handling, right? So those transactions, they're actually submitted to L1, and so that we are certain that Ether will be bridged over, very often the sequencing protocols, they actually contain some kind of a mandate that these transactions have to be included at the beginning of very first block when they were detected, and so on. So why is this important? If you come back in the future, 5 years down the road, right? What you as an independent actor in the system should be able to do, you should be able to read the data availability layer, read all the transaction, and completely deterministically rederive the state of the chain. And that's cool if you don't have any oracle that could potentially say, no, this transaction should not be included, right? Because if that oracle has disappeared, you cannot ask it. And you also do not have the guarantee that the oracle would always respond exactly in the same way. So what I am saying here is L1 deposit transactions are a little bit of a problem, but not really. They can be handled. It is just important that we check them as well because they can trigger hacks, and that we record somewhere on blockchain, somewhere on the data availability layer, the decisions of the oracle, which then needs to impact that decision whether this transaction will go onto blockchain or not. And I have 50 seconds left. This is the end of my talk. So with this, I would like to thank you for your attention. My name is Martin. You have my email right there. You have my Telegram right there. We have Twitter accounts or X accounts. The official account for the network is ZircuitL2. Me and some other engineers occasionally tweet from account Dr. Zircuit. We have pretty active community on Discord, so feel free to join. There is roughly 100,000 people who can be your friends. And last week, we also launched a liquid restaking program, which, as I checked right before this talk, has something like $350 million in locked Ether value. So if you would like to stake, maybe get some points, here is the link for you. With that, if you have any questions.